welcome to the deep dive. You ready to get a little philosophical today?
Always.
Okay, good, because we're diving headfirst into the philosophy of science.
I love it. And, it's interesting because I think most people, they think of science as all about facts and discoveries and all that, but they don't really stop to ask, how do we even know those things are true?
Yeah, that's such a good point.
Yeah.
We've got this book here, Understanding Philosophy of Science. It's by James Ladyman. And we're going to be, using this as our guide to tackle some really big, really heady questions.
Yeah.
Things like, is science truly objective? Can we ever actually prove a theory is true? How do we even tell the difference between real science and something that's just like trying to sound sciencey?
Exactly. It's almost like, how do we know what we know?
Yeah. And we're going to go on a journey through the history of scientific thought today.
Right.
Think Aristotle, Francis Bacon, Isaac Newton. We're covering some serious intellectual ground here.
Big names.
Yeah. Okay, so let's jump right in. One thing that really struck me when I was reading this book was just how much power and prestige science has, in our society.
Absolutely.
I mean, think about it. We rely on, forensic evidence in courtrooms. Doctors prescribe medications based on clinical trials. Governments make policies based on all these scientific reports. So it's kind of everywhere.
It really is.
It is, right.
Right. And I think when you look at it like that, it raises a really big question. What is it about science that gives it this, special status? Why do we put so much trust in what scientists tell us?
Yeah, it's almost like science has this, magical aura of objectivity and truth around it, right?
Right.
But before we get too carried away, I think we should probably take a step back and just define what we're actually talking about when we say philosophy of science. Right?
Yeah, good point. We need to draw some lines here.
Draw some boundaries.
Yeah. So, philosophy of science, it's not really about the ethics of science, should we be doing this kind of research or not, or the politics of scientific funding, or even the history of scientific discoveries, who did what first.
So it's not about mixing chemicals in a lab or memorizing the periodic table.
Not exactly. It's more about, examining the logic and the methods and the assumptions that underlie all of science. It's about understanding how science actually works, what makes it different from other ways of knowing about the world.
So it's kind of like philosophy of science is the referee, making sure that everyone's playing by the rules.
I like that.
You do?
Yeah, it's concerned with those fundamental rules of the game, the assumptions that scientists are making, and how those assumptions kind of shape the kind of knowledge that they end up producing.
Okay, that makes sense. So where do we even begin with all of this?
Well, one of the key areas that philosophy of science digs into is this thing called epistemology.
Epistemology. Okay, that sounds a little intimidating. Break that down for me.
I know, right? It's actually simpler than it sounds. Epistemology is just the study of knowledge itself. What does it even mean to know something? And how can we be sure that what we think we know is actually true?
Okay. I can see how that's really relevant to science, because scientists are always trying to figure out what's true about the world.
Exactly. And, one of the classic definitions of knowledge that we encounter in this book here is that it's justified true belief.
Justified true belief. Okay. So it's not enough for something to just be true, right? I have to believe it, and I need to have, a good reason for believing it. I can't just be making things up.
You got it. The book gives this really helpful example. Let's say you win the lottery. Okay, so you believed your numbers would come up, and they did, right? So you had a true belief. But did you really know you were going to win?
Probably not. Unless I rigged the game somehow.
Right. So you might have gotten lucky, but without some kind of justification, it wasn't truly knowledge.
Okay, that's a really good point. And it seems like a pretty simple idea at first, but when you actually start thinking about it, it gets really complicated really fast.
Absolutely. And this quest for a reliable method to get to this justified true belief was really, what sparked the scientific revolution.
Ah, the scientific revolution. All right, so now we're traveling back in time a bit. So we're talking about Copernicus, Galileo, Newton, some really big names in history.
Yeah, it was a time of huge upheaval in how people understood the world. Before the scientific revolution, everyone pretty much agreed with Aristotle that the Earth was at the center of the universe.
Right.
And then Copernicus comes along and says, nope, it's the sun that's at the center. And then Galileo builds a telescope and starts gathering all this evidence to support Copernicus's claim. Talk about a major paradigm shift.
Yeah. It's like humanity suddenly realized we'd been looking at the universe through the wrong end of the telescope.
That's a great way to put it. And, amidst all this change, a key figure emerges. Francis Bacon.
Francis Bacon, the knowledge is power guy, right?
That's the one. Bacon was really obsessed with finding a new, reliable method for scientific inquiry. He was all about observation and this process called induction.
So was he just, like, wandering around observing everything he could?
Not exactly. He advocated for a very systematic and meticulous approach to observation. He believed in gathering tons of data and then organizing it carefully to look for patterns and connections. He even proposed arranging observations into tables, kind of like, spreadsheets, to make those patterns easier to see.
So like a scientific detective, gathering clues, trying to piece together a mystery.
Exactly. And he believed in carefully comparing instances where a phenomenon occurs with instances where it doesn't occur. He called these tables of instances essence and presence for when the phenomenon occurs, and deviation and absence for when it doesn't.
That's so interesting. So by comparing these tables, scientists could start to figure out, like, the underlying causes of things.
Precisely. Bacon believed that through this rigorous process of observation and comparison, scientists could induce general truths about how the world worked.
That's fascinating. And his ideas had a huge impact, right? I mean, we still talk about the scientific method today.
Oh, absolutely. Bacon really laid the groundwork for the way that science is still done today, He saw science as this collaborative, systematic endeavor, which is why we have, giant research projects and international collaborations happening all the time.
So if we just observe the world carefully enough, we can kind of induce general truths about how things work. Seems pretty straightforward. What could possibly go wrong?
Well, that's where things get a little more complicated. Enter David Hume, the ultimate philosophical skeptic who throws a major wrench into the whole idea of induction.
Oh, no. What did Hume do?
Well, Hume argued that even though induction is really useful, it can't actually be logically justified.
Wait, what? You mean all that scientific data, all those experiments, might not actually guarantee anything?
Yeah, that's exactly what Hume was arguing. He said that we can't logically prove that the future will resemble the past, even if it's happened that way 1,000,000 times before.
So just because the sun has risen every day of my life, that doesn't actually mean it's going to rise tomorrow.
Well, that's the unsettling implication of Hume's critique. He pointed out that we can't prove that the universe will continue to operate the same way it always has. Our belief in this uniformity of nature, he said, is based on habit and instinct, not on pure logic.
That is, seriously mind-blowing. So is science, built on a foundation of sand? Are we just, doomed to live in a world where all of our scientific knowledge could, collapse at any moment?
Well, it's not quite that bleak. There have been many attempts to kind of address Hume's critique and come up with ways to maybe, justify induction.
Okay, good. So what are some of the ways that, philosophers have tried to kind of get around this this problem of Hume's?
Some have tried to come up with, a purely deductive justification for induction, meaning they try to prove it must be true based on logic alone.
Okay.
Others have argued that induction is at least probabilistically sound, meaning that while we can't be certain, we can at least be, pretty darn confident that the future will resemble the past.
So it's philosophers are trying to kind of shore up the foundations of science and make sure that it's not all about to crumble beneath our feet.
Exactly. And this search for a more solid foundation for science leads us to Karl Popper and his really radical solution to this problem of induction.
Okay.
And his solution is called falsificationism.
Falsificationism. Okay, sounds intense. What is that all about?
Well, Popper really flipped the whole idea of scientific proof on its head.
Okay.
He said that instead of trying to confirm our theories, we should focus on trying to disprove them.
Hold on.
Yeah.
So instead of looking for evidence that supports our theories, we should be out there looking for evidence that contradicts them. That seems completely backwards.
Yeah, it might seem a little counterintuitive, but Popper argued that this is precisely what separates real science from what he called pseudoscience. He thought that a genuine scientific theory should make what he called risky predictions.
Okay.
Predictions that could potentially be proven false.
Okay, I think I'm starting to see where this is going. So can you give me an example of this whole risky prediction thing?
Sure. So let's take Einstein's theory of general relativity. One of the things that it predicted was that light would actually bend around massive objects like the sun.
Right.
This was a bold prediction, and it could have easily been proven wrong if scientists hadn't observed it, right?
So Einstein was basically putting his theory on the line, saying, if this prediction doesn't pan out, then my whole theory's wrong.
Exactly. And that willingness to be proven wrong is what Popper saw as like the hallmark of genuine science.
I see. So instead of just looking for evidence to support our theories, we should be actively out there, like, trying to prove them wrong.
Right.
And if our theory can, like, withstand all those attempts to disprove it, then we can kind of be more confident in it.
You're getting it. And, Popper contrasted this with theories like, for example, Marxism or Freudian psychoanalysis, which he considered to be what he called pseudo-scientific.
Okay.
He thought these theories were too flexible, they were too easily twisted to kind of fit any evidence, and therefore not truly scientific.
Okay. So according to Popper, a real scientific theory should be like, I don't know, like a daredevil walking a tightrope high above the ground.
Oh, I like that.
Yeah. Always risking a fall, constantly open to being disproven.
That's a fantastic analogy, and it's this inherent risk, this constant vulnerability to being falsified that really gives scientific knowledge its power. But of course, even falsificationism isn't a perfect solution.
Oh, you mean there are problems even with this seemingly rock-solid approach?
Yeah, there are definitely some challenges to a purely falsificationist view of science. For example, it's rarely as simple as just testing one hypothesis in isolation.
Right. Science is, it's not always that neat and tidy, is it?
No, it's not. It's more like like baking a cake, right?
Yeah.
If the cake flops, it could be because of the eggs or the oven temperature or, like a dozen other things.
So it's hard to pinpoint exactly what went wrong,
Yeah.
right? You can't just be like, oh, it's definitely because I forgot the baking powder.
Exactly. And this is actually something that the philosopher Pierre Duhem, he pointed out that experiments are actually testing a whole bunch of hypotheses and background assumptions all at once.
I see. So are you saying that even when an experiment seems to disprove a theory, it might actually be that one of our underlying assumptions was wrong?
That's one possibility, and this is known as the Duhem-Quine thesis.
Okay.
And it makes it a lot harder to definitively say that we've falsified a theory.
So even with falsificationism, things are still pretty complicated.
Yeah. Well, science is complex. And this leads us to another important point about falsificationism. It doesn't really work so well with what we call probabilistic statements.
Probabilistic statements. You mean statements that say something is, like, likely to happen but not guaranteed?
Precisely. So think about, like, a weather forecast, right, that says there's a 70% chance of rain tomorrow. If it doesn't rain, does that mean the forecast was wrong? Not necessarily. It's still possible that, that 30% chance of no rain just happened to occur.
So falsificationism has a harder time with theories that deal in probabilities rather than absolute truths.
Right. And then there are also what we call existential statements, which just assert that something exists. So, like, how do you falsify the claim that black holes exist?
Right.
You can't exactly observe their absence as proof that they're not out there somewhere.
Right. So while falsificationism is a powerful tool for, like, understanding science, it's not a magic bullet that, like, solves all the problems.
Exactly. And this leads us to Thomas Kuhn and his very influential ideas about paradigms and scientific revolution.
Okay, paradigms and revolutions. Now, this sounds exciting. Tell me more.
Okay, well, Kuhn, he challenged this view that science is just this, smooth, gradual accumulation of knowledge. He said, no. Science goes through these periods of stability, what he called normal science, where everyone's kind of working within this shared framework, a shared set of assumptions and methods.
Okay.
But then every once in a while, there's this major upheaval, a scientific revolution, where the old paradigm is, like, completely overthrown and replaced with a new one.
So science isn't just a straight line from, like, ignorance to enlightenment. There are these, like, big jumps and shakeups along the way.
Exactly. And those jumps are often driven by more than just pure logic and evidence.
You mean things like social pressure or even personal biases can play a role in how, like, science actually progresses.
Right. Kuhn argued that the adoption of a new paradigm is often influenced by, social factors, the personalities of the scientists involved, and even just the availability of alternative theories.
So scientific progress can be kind of messy and unpredictable.
Exactly. And this ties into another one of Kuhn's key ideas, theory-laden observation.
Okay, theory-laden observation. Break that down for me.
Okay, so Kuhn argued that our observations aren't really purely objective. He said that our background beliefs and our theoretical frameworks, they actually shape how we interpret the data that we collect, and even what we consider to be, like, important observations in the first place.
So two scientists could be looking at the same data, but actually, like, see different things depending on their, like, pre-existing beliefs?
Precisely. Think about, how astronomers used to interpret comets. So before the scientific revolution, comets were seen as divine omens, signs of impending doom. But once we started to understand the laws of physics, comets just became icy rocks hurtling through space.
Right.
So same object, completely different interpretation based on the prevailing theory at the time.
Wow, that's a great example.
Yeah.
So even what we see with our own eyes could be influenced by, like, the theories that we already hold.
Exactly. And sometimes, Kuhn argued, paradigms can be so fundamentally different that they can't even be directly compared. He called this incommensurability.
Okay, that's a mouthful. So it's like trying to have a conversation with someone who speaks a completely different language. You might be looking at the same world, but you're interpreting it in totally different ways.
A perfect analogy. And this brings us to one of the biggest debates in the philosophy of science. Scientific realism versus anti-realism.
Okay. Realism versus anti-realism.
Okay.
That sounds like a battle of, like, epic proportions. What's at stake here?
Well, at its core, the debate is about whether we should believe that our best scientific theories actually describe the unobservable world, the world beyond what we can directly see and touch.
So the realists are like, yeah, science is giving us the real deal.
Yeah.
And the anti-realists are like, hold on, we can't be so sure.
That's a great way to put it. Scientific realists argue that when a theory makes accurate predictions and it explains a lot of different phenomena, it's because it's latching onto something true about the world, even if we can't directly observe those things.
So it's like science is, like pulling back the curtain and showing us the hidden machinery of the universe.
Anti-realists, on the other hand, they're more cautious. They argue that we can't be certain that our theories are truly describing reality. They might just be really useful tools for making predictions, but not necessarily accurate representations of what's really out there.
So they're saying that science is more like a map that helps us navigate the world, but we can't be sure that it, like, perfectly reflects the actual terrain.
Exactly. And one of the big challenges for scientific realism is something called the underdetermination of theories by evidence.
Underdetermination. Another one of those big philosophical words.
Oh, but don't worry, it's not as complicated as it sounds. Underdetermination just means that there could be multiple theories that all fit the available evidence equally well.
Oh, so like, like having several suspects in a crime, but not enough evidence to say for sure who did it.
Exactly. If multiple theories can all explain the data, how do we know which one is the one that's actually describing, reality?
Yeah, that's a good point. So how do realists respond to that?
Well, one common response is to appeal to something called inference to the best explanation, or IBE for short.
Okay. IBE. So we should just choose the theory that, like, provides the most convincing explanation, even if there are other theories that, like, technically fit the data as well.
Exactly. Realists argue that IBE is a pretty reasonable and reliable way to, choose between these competing theories.
Can you give me, like, a concrete example of IBE in action?
Sure. So let's take the germ theory of disease, right?
Okay.
We can't directly see germs.
Right.
But the theory that, that tiny organisms cause illnesses, it provides the best explanation for a wide range of phenomena, like from why diseases spread to why sanitation practices help prevent them.
So even though we can't see them, we believe in germs because that explanation just kind of makes the most sense of all the evidence we have.
Exactly. But of course, even IBE has its critics.
Of course. There's always someone ready to challenge a philosophical idea.
And one challenge comes from a philosopher named Bas van Fraassen and his view called constructive empiricism.
Okay, constructive empiricism, what's that all about?
Okay, so Van Fraassen argues that we should only believe what our theories tell us about observable phenomena.
Okay.
We can believe in, like, the predictions of a theory, but we don't have to believe in the unobservable entities that it postulates.
So it's like saying we can trust the map to guide us, but we don't have to assume that it perfectly reflects what the terrain actually looks like.
That's a great way to put it. So Van Frassen thinks that believing in those unobservable entities is going a step too far. It's a kind of leap of faith that's not really justified by the evidence.
Okay, so we're left with this really interesting standoff between, like, the realists who want us to really embrace the power of scientific explanation, and then the constructive empiricists who are, like, urging us to be a bit more cautious and remember that there are limits to what we can actually know, for sure.
Exactly. And this tension, this ongoing debate, is what makes the philosophy of science so fascinating. But we're not quite done yet. There's another layer to this whole realism debate that we need to unpack.
Another layer. Okay, I'm ready. What else is there?
So even if we kind of accept the realist position, we still have to grapple with the question of what specifically we should be realistic about.
Okay, so even if we believe that science can tell us something true about, like, the unobservable world, how do we decide which parts of our theories we should, like, really take seriously?
That's the question. And that's where we run into Larry Laudan and his argument for pessimistic induction.
Pessimistic induction. Okay, that doesn't sound very optimistic.
Well, Laudan points out that throughout the history of science, there have been tons of theories that were incredibly successful. You know, they made accurate predictions, they explained a lot of phenomena, but ultimately they turned out to be wrong.
So just because a theory, like, works, that doesn't mean it's actually true. Kind of like that old saying, even a broken clock is right twice a day.
Perfect analogy. So Laudan's point is that even our current best theories, the ones that seem to be working really well right now, could still be wrong in some really fundamental way.
So are you saying that, like, all those scientific advances, all that progress we've made might have been based on theories that, like, weren't even right to begin with? That's kind of unsettling, isn't it?
That's the pessimistic part of pessimistic induction.
Yeah.
It makes you wonder how much we can really rely on scientific knowledge if even our most successful theories can turn out to be wrong.
That's a lot to think about. Is there any way to, like, residue scientific realism in the face of this historical pessimism?
Well, there are definitely attempts to do just that. One approach is to focus on the parts of theories that have kind of survived multiple scientific revolutions.
So even though whole theories might, like, get overturned, there might be certain, like, key elements that kind of endure and carry over into the new paradigm.
Exactly. For example, the concept of conservation of energy, that's been around for centuries, and it's survived multiple shifts in scientific thinking, which suggests that it might be, pointing to something truly fundamental about how the universe works.
Okay. It's like, I don't know, like digging through the ruins of an ancient city, right?
Yeah.
Even though the buildings have all crumbled, we might still find these valuable artifacts that give us insights into the past.
And this brings up another tricky issue. This is called the problem of reference.
The problem of reference, what's that?
Well, it's the question of what our theoretical terms actually refer to. So, for example, when we talk about electrons, are we really talking about things that exist out there in the world?
Right.
Or are they just convenient concepts that we've invented to help us kind of make sense of things?
That's a really tough one. I mean, we can't see electrons directly, so how do we know if they're, like, real or just part of our model of the world?
Exactly. And then, there's also the challenge of defining what we mean by approximate truth, right?
Yeah.
So how do we know if a theory is getting closer to the truth, even if it's not perfectly accurate?
So even if we accept the realist position that, science can reveal truths about the world, there are still all these, like, deeper questions about the nature of those truths and how we can even, like, know them.
That's exactly right. And these are just a few of the questions that really make the philosophy of science such a rich and fascinating field of study.
Wow. We've covered a lot of ground in a short amount of time. Before we get completely lost in all this philosophical complexity, maybe we should take a step back and just kind of review some of the key takeaways from our deep dive so far.
That's a great idea. Let's recap where we've been and highlight some of the big ideas for you to kind of chew on.
Yeah.
Sounds good. Okay, so where were we? Right, we were talking about all the ways science shapes our world. We rely on it for so much. But then we have to ask, how do we know science is reliable? What makes it different from just, believing whatever sounds good?
And that's where we got into epistemology, right?
Yeah.
The whole idea of knowledge needing to be justified, not just a random belief. We can't just say, oh, I think this is true, so it must be.
Exactly. We need good reasons. And for a long time, induction seemed like that good reason. You see a pattern, you assume it'll continue, and boom, you make a prediction. Pretty straightforward, right?
At least it seemed that way, until David Hume came along and basically said, wait a minute, just because something happened before doesn't mean it's guaranteed to happen again.
Hume really shook things up with that. Suddenly we have to question even the most basic assumptions, like the sun rising tomorrow.
Yeah, that one really made me think. But then, didn't Karl Popper offer a different perspective with his idea of falsificationism?
Exactly. Popper said, look, real science isn't about being right all the time. It's about being testable. A good scientific theory should stick its neck out, make predictions that could be proven wrong.
So we should actually be trying to disprove our theories, not just gather evidence that supports them.
That's the key. If a theory survives all our attempts to debunk it, then we can be more confident in it.
So it's like those crash tests they do with cars. You don't want a car that falls apart on the first impact. You want one that can withstand those forces and keep the passengers safe.
That's a great way to put it. The theories that survive the most rigorous tests are the ones we can trust the most.
Makes sense. But I think we were talking about how even falsificationism has some limitations, right?
Oh, absolutely. It's not a perfect system. For one thing, you can't always test just one hypothesis in isolation. Real-world science is messy.
Yeah, it's like when you have a computer problem and you're trying to troubleshoot.
Yeah.
Is it the hardware, the software, the internet connection? So many variables.
Exactly. And that's what Pierre Duhem pointed out with his idea of what we now call the Duhem-Quine thesis. You're always testing a whole web of assumptions, not just one thing in isolation.
So even when an experiment fails, it doesn't necessarily mean the whole theory is wrong. Maybe it's just one of the underlying assumptions that needs adjusting.
Right. It's more like tweaking a recipe than throwing the whole thing out.
Yeah.
And then we also discussed how falsificationism can get tricky with probabilistic statements.
Right. Those are the ones that say there's a chance of this happening, but it's not guaranteed.
Exactly. Like with a weather forecast. If the forecast says 70% chance of rain and it doesn't rain, does that mean the forecast was wrong? Not necessarily.
It just means a 30% chance won out that time.
Exactly. And then there are existential statements which claim something exists. How do you falsify the claim that, say, unicorns exist? Just because we haven't found one doesn't prove they don't exist somewhere.
So while falsificationism is helpful, it doesn't solve everything. There are these gray areas where it's harder to apply.
And that's where Thomas Kuhn comes in, offering a different perspective with his ideas about paradigms and scientific revolutions. It's not just about individual theories, it's about those big shifts in how we understand the world.
Yes. Paradigm shifts.
Yeah.
These are like those aha moments, right? When everything we thought we knew gets turned upside down.
Exactly. Kuhn argued that science has these periods of normal science, where everyone's working within a shared paradigm, but then anomalies start popping up, things the current paradigm can't explain.
It's like when you're putting together a puzzle and you find a piece that just doesn't seem to fit anywhere.
And if enough of those anomalies accumulate, it can trigger a crisis, leading to a scientific revolution where the old paradigm gets replaced with a new one.
It makes you wonder if we're living through one of those revolutions right now. With all the new discoveries in, say, quantum physics or artificial intelligence, it feels like our understanding of reality is changing rapidly.
It's definitely an exciting time to be thinking about these things. And Kuhn's ideas really highlight how those revolutions aren't always driven solely by pure logic and evidence. Social factors, personal biases, all those things play a role too.
So it's not just about cold, hard facts. The human element is always there, shaping how science progresses.
Right. And this ties into another key idea of Kuhn's theory-laden observation.
Right. Our observations are always filtered through the lens of our pre-existing beliefs. It's like we're all wearing these metaphorical glasses that color how we see the world.
Exactly. And that raises some big questions about objectivity. If our observations are shaped by our theories, does that mean science is just a bunch of subjective opinions?
Which leads us to that epic battle. Scientific realism versus anti-realism.
That's the big one. Are our best theories actually describing reality as it is, especially the parts we can't directly observe, like those tiny subatomic particles? Or are they just convenient tools that help us make predictions without necessarily mirroring the true nature of things?
So the realists are saying, yeah, science is giving us a glimpse behind the curtain, showing us the true workings of the universe, while the anti-realists are like, hold on, we can't be so sure. Maybe we're just seeing shadows on the wall.
And that's where the underdetermination of theories by evidence comes into play. If multiple theories can explain the same observations, How do we know which one is the true one?
It's like having different maps that all lead you to the same destination. Which one is the most accurate representation of the actual terrain?
Exactly. And one way realists try to address that is through inference to the best explanation, or IBE.
Right, we talked about that. It's like saying, okay, sure, all these theories work, but this one explanation is so elegant, so parsimonious, that it just feels right.
It's appealing to that sense of, like, explanatory power. But, as always, there are counter-arguments. Bas van Frassen, with his constructive empiricism, says we should only believe what our theories say about observable phenomena.
So we can use the map to navigate, but we don't need to believe that there are little cartoon mountains and rivers hidden under the paper.
Precisely. We don't need to commit to a particular view of what that unobservable reality actually looks like.
So we have this ongoing tension between realists who want to embrace those grand explanations and the constructive empiricists who urge more caution, reminding us that there are limits to what we can definitively know.
And this leads us to another layer of the realism debate. Even if we accept that science can tell us something true about the world, what specifically should we be realistic about?
Right. Which parts of our theories are most likely to be accurate and which parts might just be, placeholders until we get a better understanding.
And this is where Larry Laden comes in with his pessimistic induction argument. He reminds us that throughout history, many seemingly successful theories have eventually been proven wrong.
It's a good reminder that we've been wrong before, so we should always be open to the possibility that we might be wrong again.
Exactly. Even our best current theories could have some fundamental flaws that we haven't discovered yet.
So scientific knowledge is always provisional, always subject to revision. It's a humbling thought.
It is. And then there's the problem of reference. What are those theoretical terms really referring to? Do electrons or black holes actually exist as things out there in the world, or are they just convenient concepts we've created?
And if they do exist, how closely does our concept of them match the reality?
Right. And how do we even measure whether we're getting closer to the truth with our theories, especially when we acknowledge that no theory is perfect?
It's like trying to capture the essence of something incredibly complex, like, the human experience. You can write poems and novels and songs, but you'll never fully capture the totality of what it means to be human.
And science is trying to do the same thing with the universe, to grasp its fundamental nature, even though we know our understanding will always be incomplete.
It's a pretty amazing endeavor when you think about it. So much to explore, so much we still don't know.
But that's what makes the philosophy of science so fascinating. It's not about having all the answers. It's about asking the right questions and being open to the mystery.
And being willing to revise our understanding as we learn more.
Exactly. So with all that in mind, where do we go from here? How does understanding the philosophy of science affect how we think about science's role in our lives?
That's the big question. Especially in this age of such rapid scientific and technological advancement, it feels more important than ever to grapple with these fundamental questions.
Yeah.
Okay, so let's do a quick recap, kind of remind ourselves where we've been on this deep dive into the philosophy of science.
Yeah, sounds good.
We started by, talking about how much science shapes our lives, all the technology, the medicine, all that stuff. But then we got into, how do we even know science is giving us, a trustworthy picture of the world?
Right. It can't just be based on blind faith. We need good reasons to trust what science tells us.
Exactly. And that's what led us to, epistemology, right? The study of knowledge itself. How do we know what we know? And we talked about that classic definition, justified true belief.
Which sounds simple enough at first, but then you start digging deeper and it gets really complicated.
Yeah. It's not enough to just believe something. You need good reasons for that belief, evidence to back it up, not just a hunch or feeling.
And for a long time, people thought induction was that key to scientific knowledge. You see a pattern, you make a prediction based on that pattern. Seems pretty solid, right?
Yeah, totally. Except then David Hume comes along and says, hold on a sec. Just because something happened before doesn't mean it's guaranteed to happen again.
Hume was such a skeptic. He really forced people to question even the most basic assumptions, like the idea that the sun will rise tomorrow just because it always has.
Yeah, that one blew my mind a little bit. But then didn't Karl Popper offer a different approach? I think it was called falsificationism.
Exactly. Popper said, look, Science shouldn't be about trying to prove our theories right. It should be about trying to prove them wrong.
So actively looking for ways to debunk our own theories.
Exactly.
Yeah.
Because the theories that can withstand those attempts to disprove them, those are the ones we can have real confidence in.
I kind of like that approach. It's like, you know how they test the strength of bridges by putting all this weight on them?
Yeah.
You want a bridge that can handle that stress, not one that collapses at the first sign of pressure.
That's a great English. The theories that can survive the most rigorous tests are the ones we can rely on.
Makes sense. But I think we also talked about how falsificationism isn't like a perfect system, right? There are some tricky areas where it's harder to apply.
Oh, for sure. For one thing, in real-world science, it's rarely as simple as testing a single hypothesis in isolation. There are all these other factors involved.
Like when your internet goes out at home. Is it the router? Your computer? The service provider? It can be so hard to isolate the problem.
Exactly. And that's what Pierre Duhem pointed out. He said that experiments are really testing a whole web of assumptions, not just one thing in isolation.
So even if an experiment fails, it doesn't mean the whole theory is wrong. Maybe it's just one of the underlying assumptions that needs to be adjusted.
And then we also talked about how falsificationism can have a tough time with probabilistic statements, the ones that say there's a chance of this happening, but it's not a certainty.
Right, like weather forecasts. If a forecast says 70% chance of rain, and it doesn't rain, it doesn't necessarily mean the forecast was wrong.
Right. It just means the less likely outcome happened. And then you've got existential statements, the ones that just assert that something exists. How do you disprove the claim that, say, aliens exist?
Just because we haven't found them yet doesn't mean they're not out there somewhere in the vast universe.
Exactly. So while falsificationism is helpful, it's not a magic bullet that solves every problem in the philosophy of science.
Okay, that makes sense. And then, didn't we move on to Thomas Kuhn and his ideas about paradigms and scientific revolutions?
Yes. Kuhn offered this whole different perspective on how science works. He said it's not just about individual theories, it's about these big shifts in our overall understanding of the world.
Those paradigm shifts, those are like the earthquake moments in science, right? When the whole foundation of what we thought we knew gets shaken up.
Exactly. Kuhn said science goes through these periods of what he called normal science, where everyone's working within a shared paradigm, a shared framework of assumptions and methods, but then anomalies start to appear, things that the current paradigm can't explain.
It's like when you're working on a jigsaw puzzle and you find a piece that just doesn't seem to fit anywhere, and at first, you might just try to ignore it or force it into place.
But if you find enough of those misfit pieces, eventually you have to start questioning whether you're even working with the right puzzle.
And that's when a scientific revolution happens, right?
Yeah.
The old paradigm gets overturned and a new one emerges.
And Kuhn's big insight was that those revolutions aren't always driven purely by logic and evidence. Social factors, personal biases, those things play a role too.
So it's not always this purely objective, rational process.
Right. There's a human element to it, which makes it even more interesting, I think. And then there's Kuhn's idea of theory-laden observation.
Right. The idea that our observations are always filtered through the lens of our pre-existing beliefs and theories.
Exactly. It's like we're all wearing these invisible glasses that color how we see the world, even in science.
And that leads us to that big debate we were talking about. Scientific realism versus anti-realism. Do our best scientific theories actually give us a true picture of reality, especially the parts we can't directly observe, or are they just, useful tools for making predictions without necessarily being a perfect reflection of how things really are?
It's one of the biggest and oldest questions in the philosophy of science, and we explored some of the key arguments on both sides.
Like the idea of inference to the best explanation, where we choose the theory that provides the most elegant and comprehensive explanation, even if there are other theories that could technically work.
And we talked about the challenges of underdetermination, where multiple theories could all fit the available evidence equally well.
Right. It's like having several different suspects who could have committed a crime, but not enough evidence to definitively pin it on any one of them.
Exactly. So how do we know which theory is the true one if multiple theories can all explain the observations? It's a tough question. And even if you lean towards realism, there's still that question of what specifically you should be realistic about.
Right. Like, which parts of our theories are the most trustworthy, the most likely to hold up over time? Because we were talking about how Larry Lauden's argument for pessimistic induction reminds us that even very successful theories can turn out to be wrong in the long run.
Exactly. Scientific knowledge is always provisional. We have to be open to the possibility that our current understanding might need to be revised as we learn more.
It's kind of a humbling realization, isn't it?
Yeah.
That even our best scientific theories could have some fundamental flaws that we're not aware of yet.
But I think it also makes science even more exciting. There's always more to discover, always more to learn. And then, of course, we can't forget about the problem of reference. What are all those theoretical terms really referring to? Like when we talk about electrons or black holes, are those just convenient labels we've given to things, or are they pointing to something real that exists out there in the universe?
And if they do exist, how closely does our mental picture of them match the actual reality? It makes you wonder if our language, our concepts, are even capable of fully grasping the true nature of things.
And that ties into the whole question of how we define approximate truth in science. If we acknowledge that no theory is ever perfect, how do we judge whether we're moving closer to a more accurate understanding?
These are some really deep questions. It's kind of like the more we learn about science, the more we realize how much we don't know.
But that's the beauty of it, isn't it? Science is an ongoing process of discovery, and the philosophy of science helps us understand the complexities and the nuances of that process. It's about asking those tough questions and being willing to live with a certain degree of uncertainty.
I think a key takeaway for me is this sense of humility. Science is incredibly powerful, but it's also fallible. And I think that's okay. It doesn't diminish the value of science, it just makes it more human, more realistic.
Exactly. Science isn't about having all the answers. It's about being curious, being open to new ideas, and being willing to constantly revise our understanding as we learn more.
That's a great way to put it. So I guess the big question now is, where do we go from here? We've explored all these complex ideas about the nature of scientific knowledge and the challenges and limitations of science. How do we apply this understanding to our own lives?
I think it starts with being more aware of our own assumptions and biases, recognizing that even the way we see the world is shaped by our pre-existing beliefs and theories. And then I think it's about being willing to engage with science in a more critical and nuanced way.
Not just blindly accepting what we're told, but really thinking about the evidence, the methods, the underlying assumptions.
And being open to the possibility that what we consider settled science today might be overturned by new discoveries tomorrow.
That's what makes science so exciting. It's a journey, not a destination. And the philosophy of science gives us the tools we need to navigate that journey more thoughtfully and critically.
Well said. I think that's a great place to wrap up our deep dive into the philosophy of science. We've covered a lot of ground today, but this is just the beginning of the conversation. I hope this has sparked your curiosity and given you some new perspectives on how science works and how we can all engage with it in a more informed and meaningful way.
Yeah, definitely. This has been a great conversation. And remember, folks, even though our deep dive is ending, the journey of discovery never really ends. There's always more to explore, more to learn, and more to question. So keep those curious minds engaged, and we'll see you on the next deep dive.